know what you're doing with cross product. And you can write out the determined cross product, but you can really do this without doing so. I don't care if you do, it's okay. I can live with that. But you have cosine theta multiplied by the quantity b minus a cosine theta. And this corrects something that I didn't like before. I really wanted a cosine squared plus a sine squared here. I wasn't getting it. So, and I mentioned that in class. I didn't like that, but I went with it. Okay? It's going to simplify things a bit, but of course that's going to give us a 1. Well, okay. We do cosine theta times b, we get b cosine theta. We do cosine theta times negative a cosine theta, we get negative a cosine squared theta. Now we still have the minus out here because j cross I is negative k. Well, when we do that, everything simplifies as I've written it, except that now I have this thing that I was kind of hoping for in the first place. I have a plus here, so this whole cosine squared theta plus sine squared theta becomes 1. But since I've got it written out, I'm going to continue to write it out, and then I'll kind of correct it down here. I'll just get rid of it because a times 1 is a. So we're going to have a plus b cosine theta in our integral. Now, we're not there yet. But we're about there because now I've got all this, and I've got this whole thing to the 3/2. I'm just carrying it along at this point. Because I know I'm going to be able to simplify it, and it doesn't involve a delta L, so when we approach our integral, it's just going to kind of go along for the ride. Okay, well, if we sum up all of our delta B's and let our delta L's approach 0, so that we approach an integral, what integral are we going to approach? K prime I is a constant, it's going to come out in front. Now our dl is ultimately going to be expressed as a d theta, okay? So that we have an integral in terms of theta, so we can integrate all these thetas, because that's really what we're after. So I write that out here. Our dl is really a d theta. So the dl needs to go inside our integral. It's really our variable of integration, but we're going to change it to a times d theta. Everything else goes along, the numerator and the denominator. But now I've simplified the denominator, and you can easily square this and add this. You're going to get a b squared, I think I actually do that, b squared minus 2ab cosine theta from the cross product term here. And then you're going to have an a squared cosine squared theta to add to the a squared cosine squared theta you get here. Now that should officially be a negative a, but I've not bothered with the negative because it's inside a square. Okay, well, we're then going to have the b squared minus 2ab cosine theta that we get here, but then it's going to be an a cosine squared theta plus an a sine squared theta. Cosine squared plus sine squared is 1, so we just get an a squared. Okay? Now, the only thing I need to change here, and it simplifies things a little bit because I no longer have a difference of cosine squared and sine squared, which is going to be related, which would have been related to the cosine or the sine of 2 theta. I can just get rid of that. And I just have a plus b cosine theta. I'll make that change right here before your very eyes. It's going to get a little bit dusty there. But I'm just going to write that then as a plus b cosine theta. Well, there's our integral. That is the magnetic field. If I've done everything else correctly, that is the magnetic field at distance b from the center, the magnitude of the magnetic field. And as we saw, the magnetic field is out of the loop if we're going counterclockwise around the loop. Right-hand rule tells us the direction of every I delta L cross unit vector R. So it's going to be the direction of the sum as well. Now we want to compare this integral. And you can do the integral. I'm kidding. I don't think I can do the integral. Although the fact that we have something like a law of sines here, cosines here, makes it possible that we might have a way of doing the integral. I recall this as being an impossible integral, but I'm going to play with it and see. If it isn't impossible, I'm going to think I probably made a mistake. Okay, anyhow, we compare this integral with mu naught I over 2a. Okay? Now remember that mu naught and k prime are just related by the constant 4 pi. So k prime is mu naught times 4 pi. Because of the flux, or the line integral stuff. So, I'm probably going to end up having to do this integral as a numerical calculation. And I'm going to call this, now I kind of had an unfortunate choice of distance from the center. I'm going to, A was the radius, so I'm going to let little b be the distance to the center, but now I got magnetic field B as a function of little b, so I got B of B. It's maybe a little unfortunate, maybe I should have used a different variable here, but I could change the name of the distance from the center, and all I'd have to do is change it here, here, and here. So, this is a magnetic field as a function of B, the distance from the center. Maybe I'll let that distance be x. But that kind of invokes the x-axis and confuses the rotational symmetry thing. Okay, well, more about that in a minute.